So thanks for coming. My name is Dennis Gove. I work at Bloomberg LP, and I'm a Solr committer. Today, I want to talk about how to create new Solr stream classes. If you're not familiar with what Solr streams are, we'll take a look at sort of their concept and how you can use them. And then we're going to jump into how to actually write the code to create new streams. Just a note about Bloomberg, we're the largest provider of financial news and information. Our strength really is to quickly and accurately deliver the data, the news, and analytics on top of that data. And then to do that, we need to create high performance and accurate information retrieval systems. Solr is one of them. We use Solr extensively in our company. Okay, so what's our goal today? We're going to explore what Solr streams are and how you can extend the functionality to solve problems at your organization. Right now, there are 30+ streams in existence that I know of, but that is nowhere near the breadth of functionality that you can accomplish with them. And there are a lot of problems out there that none of us working on streams have even conceptualized. That's why we've tried to make it as easy as we could to extend the streams that exist. All right, so our agenda is just, we're going to look at Solr streams and expressions. We're going to take a look at the expression structure. This is sort of an important part for how you create these streams. And then the core pieces of every stream class, and I don't want to scare you with that. The core piece is very, very small. It's just a few functions. And then we're going to take a look at the read function through 3 examples. The read function is really where all of the work for your stream class is done. All of the other functions, except maybe 2 others, are just kind of metadata style functions to help the stream classes function properly, but your business logic lives in your read function. And then we're going to see how you can expose those streams in Solr, and there are 2 ways in which you can do that. All right, so this is the definition of Solr streams and expressions from the reference guide. I'm going to read it because it's a little complicated. Stream and expressions provide a simple yet powerful stream processing language for Solr Cloud. They're a suite of functions that can be combined to perform many different parallel computing tasks. It's a little dense. When I read that, I'm like, I don't quite grasp it. In my sort of view, a Solr stream is just a pipeline of actions that you perform over a set of tuples. And you can think of tuples like documents in a Solr collection, but they're not exactly the same thing. They're just parts of a document. And they might be documents that were created as part of your stream, right? So when we're looking at this diagram here, and this I just clipped from the admin page, because on the admin page you can execute streams and view their structure. The data starts on the right-hand side where you have the data store, which is just a Solr collection called pets in this example. And then you execute a source stream, which is the search stream. And then you have a stream decorator doing a rollup. And rollup is just really a group by in database world. But the data flows from right to left. And then the expression that describes this stream is relatively simple. You can see we have a search expression, and this is just executing a search against a Solr collection. And you can see the first parameter there is the name of the collection, pets, right? And then you can provide all of your same query parameters, the queue, FL, sort, et cetera, to get your originating set of data out of your collection. And on the bottom right, you can see what the tuple looks like at that point. It's just for every record that's coming out of the collection, it's just the fields that you've asked for. In this case, owner ID and the age of the pet. Then that gets piped into a rollup stream. And like I said, a rollup is just a group by. So we're doing a rollup over the owner ID. So we're taking all the pets owned by the same person and grouping them together. And then we're calculating some metrics on that. We're getting the minimum age, the maximum age, and the number of pets that they own. And you can see this is what the tuple looks like at the end of that rollup stream. So you can see how the tuple changes as it goes through the stream. All right. One of the fundamental features of streams is that they are composable, meaning you can put streams inside of streams to solve really complicated questions that you have. In this case, we're doing an inner join between the rollup on pets that we're looking at and another collection that may exist in the same cloud, doesn't have to. And you can see our originating rollup collection, or rollup stream. And Then we're executing another search against the people collection. And we're just asking for people aged 25 to 40 living in Massachusetts, Rhode Island, New Hampshire, and sorted. You had a question? Yeah, that's actually a very good point, and I left it off here for space reasons. The default request handler in search expressions is the select handler, and if you know the select handler, it only returns a certain number of documents every time. The more performant handler is the export handler. So, if you added a qt equals export, I think it's /export, it'll use that handler instead. There's no functionality difference, just the speed and how much data you can get out is important. All right, so now we have two streams of data coming through people and our pets. And then we can join those together. And this is, it's called inner join because it really is like a database join kind of thing. And we're just joining on where the owner ID in the first stream equals the person ID in the second stream. And then the end result of that is a tuple that has the owner name and then all of the rolled up information about their pets. We can make this even more complicated if we want to. So it's election season. Let's imagine we were a consultant on a campaign and we wanted to figure out a donor list. And for whatever reason, we were looking for dog owners in Massachusetts, Rhode Island, and New Hampshire, age 25 through 40, voted in at least one presidential primary since 2008, but we don't care about anyone who's donated more than $50 because they're probably not going to give us more money. So you can see we've got our people search, right? And that's what the tuple looks like coming out of that. When we execute the inner join, which we looked at on the previous slide, you can see what the tuple looks like coming out of that. So we've got these people, their pets, right? Because maybe it was part of the conversation when we call them, we want to talk about their pets. Hey, tell me about your 3 dogs, things like that. And then we want to find out everyone who's voted since 2008 in a presidential primary. Let's say we have a collection with voting records in it. We can just do an intersect on that search. Say, only give me the people that exist in both sides, right? So that's pretty simple. And then we want to exclude anybody who's donated more than $50. The data for this exists in a database. It doesn't exist in Solr, right? We can pull data out of any JDBC available source using the JDBC stream. And you just give it a SQL statement like you would any other JDBC call, and it gives you the data in a stream format. And then we can pipe that into a complement stream, which just says exclude anybody that exists in this second stream. So the end result is we have our donor list, right? And if you needed to, you can make this more complicated, pipe things more into it. There are some things there are some things this can do that I'm not touching on for to make it more performant. If you have huge data sets, there's parallel streams and whatnot. But for time reasons, I'm not going to jump into those right now. OK, so let's take a look at what the expression structure is. And we looked at a couple of examples of expressions, and the fundamental structure is very, very simple. You have a function name, and then you have parameters within that function. And there are 3 types of parameters. There are positional parameters, named parameters, and then typed parameters. So let's take a look at what the function name is. This is really just a way for you to map some string name to the class that implements that logic. And you can see in our example, we have an update stream, which is updating some collection based on the tuples that are coming out of the rollup. We have a rollup stream, and that's just the function name that's mapped to the rollup stream. These these function names could be anything you want. You could call them ABC. It's just a mapping. We like to make them clear for the user, so if you can, call them what they mean, but you don't have to if you don't want to. One point I want to make is the function names are not just describing or representing streams. They represent other entities in this world of streaming. And you can see that with the min, max, and count parameters right there in the rollup. So what we've done is we've mapped the min function name to the min metric class. And the min metric class is what has all of the logic in it to calculate the min of some group. So what that means is you can create new metrics if you wanted to that do some classified business logic at your company. And all the user has to do is provide that metric in their function, and they don't have to do anything else. So those are function names. Positional parameters are more of a convenience. They're really mostly used for collection names. When you have a expression where you're updating a collection, or you're in some way touching a collection, pulling data out, or whatnot. Generally, we just put the collection name as the first parameter, so it's positional. All the other parameters have to exist after that. We could, if we wanted to, have collection name equals the pet owners or whatnot. But for convenience, because I didn't want to have to type that out every time I was creating these, I just put in positional parameters. Named parameters are pretty self-explanatory. These are just parameters that have any name you give it. Doesn't matter what the name is, make it somewhat descriptive. So in the update expression, we have a batch size. So every 5 tuples that come out, we're going to send it to the destination. Excuse me. The destination collection. In the rollup, we're giving it the over parameter. What field are we actually going to do the rollup over? In the search expression, we have named parameters, but we don't care what the names are. Anything that has a name in the search, we just pass on to Solr. And what this allows is, in the search expression, you can provide any parameter that Solr accepts. And if Solr tomorrow decides they're going to accept this new parameter, the implementation of this expression doesn't need to change at all. All right, so type parameters. These can get somewhat confusing to think about a little bit. There are expressions, and really almost all expressions have the concept of I need a parameter in here that represents something else, right? And what that thing is doesn't matter, but it represents something else. In this case, the update expression needs a parameter that represents a stream because it needs a stream incoming to it so it can pull records off of it. So in the implementation of the update stream class, we just say, I'm expecting some parameter that represents a stream. In the rollup expression, we have the same thing. We're expecting one parameter that represents a stream, and we're also expecting any number of parameters that represent a metric. We don't care what types of metrics they are. We just care that they represent the metric. And we'll take a look at sort of what that means as we go through. But type parameters are really powerful for you because you don't have to give them names. You don't have to give a defined size of how many you expect there to be. You just have to say, I need something of this type. I don't care what it is. All right, so let's take a look at the core pieces of every stream. We're going to take a look at the rollup stream for a little bit, just because a couple of its functions are kind of interesting. The first thing you want to do is every stream class has to extend the tuple stream abstract class. There are some utility functions in there, but almost everywhere streams are working with other streams, they're using tuple streams. They're not using any particular type of stream. It's just anything that's a tuple stream, we're OK with. And then we have to implement the expressible interface. The expressible interface gives you the get stream sort to expression and 2 explanation functions. Those are important for turning things into expressions, and then the explanation function is useful for the admin page, and we'll take a look at what each one of those does in a moment. All right, so in the constructor, you do have to, in your class, and this is something, when I was putting this together originally, I sort of waffled back and forth on for a little while. Do I want to require a particular constructor, or do I want to have like a setter function or whatnot? I decided to go with a constructor. So you have to provide a constructor that accepts a stream expression. I want to be very clear. A stream expression is an already parsed instance of this expression string that came in. You don't have to do any parsing, right? You don't have to say like, oh, I expect there to be a parentheses here and a closing parentheses and whatnot. This is already parsed for you. What you're getting is an object model of your expression. all right? And then there's a stream factory. This has some utility functions in it, which we'll take a look at for building streams and metrics and things like that. There's a lot of functions in there. Some of them are named kind of weird, and sorry about that, but I don't want to rename them now. So the first thing we want to do is pull all the parameters out. And for brevity on the slide, I extracted these out to other private methods that we'll take a look at in a second. But first, we want to get the incoming stream. So this is sort of clear that the rollup stream is expecting a stream to come into it. So it is not a stream source. It's not touching a data store. It's expecting there to be a stream that it can get the next record out of. And then it's expecting some list of metrics. It doesn't care how many. And then it's looking for the over parameter, because the rollup expression, you need to know what field or fields you're going to do your rollup over. All right. And then in the constructor, I always like to validate the parameters that came in. Did I get anything that I wasn't expecting? If I did, the user might be doing something slightly wrong, so I error out at that point. You don't have to, but I tend to try to error out as fast as I can so the user doesn't get incorrect data. All right, so the extract stream method. Now this isn't part of any of the abstract classes or interfaces. It's just I separated it out into a slide for simplicity. So the first thing we're going to do is we're going to get the expressions. We're going to get the parameters from the original expression that represent a stream. And the way we're going to do that is there's a function in the factory called get expression operands representing types. Very wordy, kind of, not clear exactly what it's doing. But the representing types is the important part. So what we're doing is give me all the parameters that represent the types that I give it at the end. It has to be expressible, and it has to represent a tuple stream. I don't care what tuple stream it represents, but it has to represent that. So if we think about our rollup stream example before, the search expression that was in that would come back because the search represents a tuple stream, all right? And then we're going to validate, because a rollup stream only expects one stream to be in there. If the user gives us two or they don't give us any, we're going to error out. And then we're going to construct the stream. And this is one of those places where you're like, oh, that's going to be really hard because I have to dynamically know what class I'm going to call based on the function name and whatnot. The factory has a function that does all of that for you. So you just give it the expression, and it'll look at the name of the function, figure out what class implements that, and then construct an instance of that, right? And how does it construct an instance of that? It calls the constructor of the stream that was passed in, right? That's why we have to provide a constructor with that signature. And it's just going to return that stream. All right, so this is a valid tuple stream that we can then use. Okay, so extract metrics. This is sort of going along the same path. We first want to get the parameters that represent metrics, right? So again, we're calling the get expression operands representing types. And we're looking for types expressible and metric, right? So this is only going to return the parameters that represent metrics. It's not going to return the parameter that represented a stream because we're only looking for the ones that represent metrics. And then we're going to take those expressions, and there could be 0, 1, 10, 20, we don't know how many there are. And we're just going to iterate through all of them. And we're going to call factory.constructMetric with the metric expression. And again, that's going to look at the name of the metric, figure out what class implements it, and then construct an instance of that by calling the constructor for that class, and then return it to you. So we just add that to our list of metrics. Okay, so the extract over is pretty simple. It's just a named parameter. So the factory has a method called getNamedOperand, right? We give it the expression and what the name is. And then it's going to give us a stream expression named parameter. And then we're just going to get the value out of that, because this is, for sample's sake, let's imagine that the rollup stream only accepts a single field that it's going to roll up over. In the real code, it can accept multiple fields, but for this, we'll just pretend it's one. So it's expecting, it'll get just a string that's the field name, and then return that. And that's pretty simple. So now we have our incoming stream, all the metrics that we want to calculate, and the field that we're going to do the grouping by, right? So now you don't have to worry about the expression anymore. You're done with it. You've already pulled your parameters out, and you can kind of forget that expression ever existed. So you now have a valid instance of your stream class, which can do all of the work that you're going to implement in the read function. But I do want to take a look at some of the other sort of metadata or helper functions that exist, and you will have to implement in your classes. The first one is open. Basically, when a request comes into the stream handler or anywhere it's being executed, you create your stream pipeline, and then you have to open all of those streams. And when you're dealing with decorator streams, and the rollup stream is a decorator because it's not touching source data, really, most of the time, all you have to do is tell its incoming stream to open. So that open call just gets passed all the way down. For the search stream or any data source streams, there's a lot more work going on there. You might have to make a connection to Zookeeper, make a connection to the data source in the JDBC stream. You got to make a connection to the database, et cetera, et cetera. Close is just doing the inverse of whatever you did in open so that you clean up your space. So in this case, we're just telling the incoming stream to close. All right, so set stream context. A stream context is the way in which other parameters that you might pass in your stream query get passed down to all the streams, right? So you know how there's the debug parameter that you can send into a search and whatnot. That would go into the stream context, and then if your stream is like, oh, if debug is turned on, I want to print some extra information out, it could turn that functionality on here. In this case, for simplicity's sake, we're just passing that on down to the incoming stream. You don't want to forget to do that, because some of the streams use that to pass information back and forth, one of them being the parallel stream. In the parallel stream, when it's breaking work across a bunch of workers, it needs to know which worker it is, and that comes in the stream context. So you definitely want to pass that along, because there might be a parallel stream further on down in the pipeline. The children function just returns what streams this stream class is acting on. So it's just a list of all your incoming streams. For the rollup, it's just one stream, but if we were looking at the inner join, there would be two streams there, and so on and so forth. The get stream sort is, I find kind of interesting, because what this allows us to do is validate the order in which tuples are coming out of our incoming streams. There are certain streams where the order of the tuples coming out is very important. The rollup stream is one of them, right? So the rollup stream is expecting the incoming data to come in sorted by whatever the field you're doing the grouping over, right? So we're expecting this to be sorted by owner ID in the example we've been looking at. In logic, or I'm sorry, in where we have our business logic, we can check that, and we can call the stream sort, and that will tell us what's the order that data is coming out of this incoming stream. If it's invalid, if it's not the order in which we're expecting, we can error out, right? What that allows us to do is fail before we give back bad data, all right? And I think that's an important thing to do. Is I don't want to start giving back data and then realize I'm giving back incorrect data. So let's fail before we give anything back. Okay. The toExpression function, this is doing the inverse of what the constructor was doing. It's taking your instance and converting it back into a stream expression. Now, it's not converting it into the string representation of that, just the object model in the stream expression class. So the first thing we do is create an instance of the stream expression, and the constructor of that expects you to give it the function name for this stream. And we're going to use the factory get function name for our current class. We're not going to hard code it here because it is possible for people, and we'll show you later, it is possible for people to rename the function that you've given to your class. So we're just going to dynamically get it at runtime when we need it. The performance cost of this is negligible. Negligible meaning it really doesn't exist. The next thing we're going to do is we're going to add the stream, the incoming stream, as a parameter. So to do that, we just call the toExpression function of the incoming stream, right? This is one of the reasons why all the streams have to implement the toExpression, so that we can just keep calling it all the way down. And then we now have a parameter that looks like the incoming stream. And then we want to add the over parameter, and this is relatively simple. We're just adding a named parameter called over, and we're giving it whatever the over value is. Now, it doesn't really matter. I think that function accepts strings and integers. There's a little overloading there. If not, just, if you have integers or doubles or whatever, you can just convert it to a string. The stream expression name parameter will know if it needs to quote the value, right? So for named parameters, sometimes the value has to have quotes around it, and sometimes it doesn't. Generally, my rule of thumb is if the value has a space in it or any non-alphanumeric character, I'm going to quote it. The implementation of stream expression name parameter knows whether or not to put quotes around something. So you don't have to worry. And if you have quotes in your value, it'll escape them and whatnot. So you don't really have to worry about any of that. For the metrics, we're really doing the same thing again, right? We're just calling metric to expression and adding that as a parameter to the expression we're going to return from us, and then we're just going to return it. So after you've implemented this, your class can now take its instance and give back a valid expression that represents that class. And you could then, just go back and forth. Say, all right, give me the expression, now construct an instance of it. Give me the expression to test, make sure it's doing the right thing. All right, the explanation function, I was kind of iffy if I was going to mention this, but I do think it's important. This allows the admin page to function. If you haven't seen it yet, I believe it was Solr 6.0, it might have been 6.1, in the Solr admin page, right under where you can execute just a Solr query and put in all the parameters, you can ask to execute a streaming expression. And there are two things you can do with that. You can execute it and get your data back, which is great because you can see you're getting the right data back. But you can also view the pipeline as nodes on a graph, right? So you can see how the pipeline sort of goes, or how the data sort of works through the pipeline and what it looks like. Because sometimes when you're looking at really complicated expressions, it can be hard to visualize it. I found that is an easy way. And the graphs that we were looking at earlier, the pipelines we were looking at earlier, I just ripped straight off of the admin page. All right. So in this function, what we're going to do is just create a new instance of the explanation. We're going to tell it that one of the children is the incoming stream, and we're just going to call its toExplanation function to iterate down on it. And then we're going to give it what is the name that's associated with this stream, the function name. We're going to tell it what class implements this, because that can be useful on the admin page. If somebody is renaming functions to different classes, you can tell them, you're using the rollup stream class and not my rollup stream class, which is the one you're expecting, which could indicate to them that they've done some mapping incorrectly. And then we're going to tell it that it's a stream decorator. Like I said, there are decorator streams, there are source streams, and there are data sources. This one is a stream decorator. And then we're going to just put into the explanation what the expression was for this, so that somebody can visually take a look at it on the admin page. And then we're going to add all the metrics as just, these are helper things on this stream, so that if you go to I believe it's on the tooltip of each node on the admin page, it'll tell you, hey, these are the metrics that you're using here. Right now, this function is really only used for the admin page. The intention at some point, and I make no promises when this will exist, but the intention at some point is to allow us to when a streaming expression comes in, to look at it and say, this isn't going to perform well, but if we change it a little bit, it'll perform a lot better, right? Let's do a inner join before we do a sort, things like that, right? None of that exists, but there's intention to add it. The explanation function will make that a little bit easier to implement. Okay. So now let's take a look at the read functions. Like I said, the read function is really where all of your business logic exists. And we're going to move away from the rollup stream, because the read function for the rollup stream is a little complicated, and I couldn't fit it on the slide. But on the final slide, there's a link to the GitHub file in the master branch for the rollup stream. So you can just take a look at that. It's kind of interesting, because it does a bit of logic. So if you want to look at that, I would suggest it. So let's imagine we're creating a stream called tuple number stream. And really, all this is doing is adding a number to the tuple as it comes through, because we want to know this was the first tuple, this was the second tuple, this was the third tuple, et cetera, right? And this is what the expression would look like. It takes one parameter, some stream coming into it. We don't care what stream it is or what type of stream it is. It just has to be one, and it doesn't take anything else. What does the read function look like? It's very simple, right? All we do in the read function is we read the next tuple off the incoming stream. We then increment our current number. We add that as a field to the tuple, right? Because you can modify these tuples as they go through. They're not static. You can add fields, you can delete fields and whatnot. We add a new field to it, and then we return that, right? There's an important point here. We're reading one tuple we're reading one tuple from our incoming stream, and we're returning one tuple. So it's a one-for-one kind of map in. And we're not throwing any tuples away. We're not collapsing any tuples down. We read it in, we send it out after we've modified it. So it's very simple. Random drop stream. Let's imagine we're doing some kind of AI training, and we just want to randomly drop some of our training data. And we want to allow the user to provide us a drop rate, right? So in this, we accept a stream and a drop rate, right? The drop rate is telling us we want to drop randomly 40% of our tuples. We don't care which ones are dropped, we only want to get 60% of whatever's coming out of the search, all right? And you can see this is just a named parameter, and it's not quoted. I guess periods don't need to be quoted, but it's not quoted, but you could, when the user writes the expression, could quote it if they want to. It doesn't matter. This read function is a little more interesting, because what we're going to do is read the next tuple off of the incoming stream, and then we're going to decide if we actually want to return that tuple. There are two things we want to check. First is this the last tuple from the incoming stream? If it is, we're done. We're just going to return it because it's the EOF tuple. And I should mention, at the end of every stream, there's a special tuple called EOF, so you know you're at the end. You've read everything. If you don't see EOF, you haven't read all of your tuples. We then want to make sure, just randomly select some doubles between 0 and 1, and if that's less than our drop rate, we want to read the next tuple off of our incoming stream. Effectively, we're going to drop the one we just read. And we're just going to iterate until we find one that we've decided not to drop. Once we find one we don't want to drop, we're going to return it. There's an important point here is for every tuple that you read off the incoming stream, you don't have to return a tuple to your user. But you do have to find a tuple you're going to return before you return from your read stream, which means you have to look at your incoming stream until you found a tuple you want to return to your user, all right? So we could iterate in this while loop 1,000,000 times before we decide, yep, we found one we want to return. And that just depends on your business logic of what are you doing with tuples. In the rollup stream, we're going to read all the tuples that match for a particular owner, and then we're going to calculate their metrics, and then we're going to return one tuple out. So you could have 10 coming in, and then just one coming out. Yeah. I'm sorry? No, you cannot. Yeah, so the read function is only going to return the next tuple. That said, and this is a caveat to my answer of no, you cannot do that. You could, if you wanted to, read the next tuple off the incoming stream, hang on to it in some kind of list internal to your class, and then return anything else that you want that represents a tuple. This is done in I forget what stream it is, but at the end of the stream, when we read the EOF tuple, we say, oh, we've got the end of the stream. We now have this metadata of like how many tuples we've seen and some other information about it. We're going to return that first. And then when they call read again, all right, now we're ready to return the EOF tuple. So you could have an incoming stream that has 10 records, and if your business logic says, let's just insert random tuples in the middle, you could do that if you wanted to. That said, you cannot return more than one tuple on every read function. Yes.
I think this is a very powerful concept using streams. How does it work in the scenario where there are multiple shards, distributed shards? Do we need to read all the streams?
No. Nope. When you have distributed shards, even if those shards exist across hosts, across data centers, or, in different AWS segments or whatever, the search stream knows, let's get all the tuples from all of the shards and pull them back. You don't have to worry about any of that.
But that means that all the shards needs to be read, and one merger will actually read all the data to get like the 40%.
In a very naive case, yes. With the parallel stream, you can actually spread that out. So if you have 10 shards, you could have 10 workers reading data off, read data off of one shard, and any of the replicas for that shard, it doesn't matter. And then each worker is only working on 1/10 of the data. And then you only bring it back together when you want to.
But that's like map reduce where you are actually shuffling the data over.
To an extent, yeah.
All the data will be shuffled and all the data will be used. It's actually completely different from the Lucene level things which we used to do where each shard was actually doing their jobs and then the merger is actually reading only the data which is required.
It's not doing a full reshuffle because it doesn't have to send the data out, right? To workers. The workers only pull the data that they care about from the shards. And the worker can exist in the same shard that you're pulling data from. So your data is not even moving across the network at that point. Only when you eventually want to bring it all together will you have to pay that network cost. But yeah, there is cost to it. It's not, it's not absolutely free. Yeah. Yeah, so when I put these slides together originally, I had a filter in there, but I didn't have time to implement it. So I didn't want to put it in there. I do intend to create a filter stream, but if somebody wants to do that for me, great. Yeah.
If you had aggregations like some count, which could be done at each of the shard nodes,
Yep.
and then push only those aggregate metrics,
Mm-hmm.
and then the leader would merge them again.
Yep. I believe if there isn't already, there's a ticket for merge stream. I think so. Joel would correct me if I'm wrong. But there is intention to be able to do that. So you can do your partial metric gathering on each worker. That gets complicated with metrics that you can't do across workers, but it can help you in a lot of cases, yeah. Okay. I skipped so a concatenate stream, this is just to show you how you can read values out of your tuple and then and use them in your read function. So in here, what we're doing is we're taking two fields, left and right field, and whatever the value is, we're just concatenating those together. And then we're gonna add that to the tuple as a new field. And it's relatively simple. You just read the incoming tuple, make sure it's not the last one, make sure it contains the fields you're gonna pull the values out of, and then we just concatenate them together. It's a relatively trivial example. Okay, so how do we integrate with Solr? And I'm running a little low on time, so I'll try to go through these pretty quickly. The first way, if you're committing your stream back to the Solr code base, this is the way you want to integrate. Inside the stream handler class, in the inform function, this is where we map the function name to the implementing class, right? So tuple number is mapped to tuple number stream.class, random drop, et cetera, et cetera. This allows the stream factory to know what function name maps to which class and which constructor does it need to call, all right? And this is the list of all the streams that exist right now. I'm pretty sure this is outdated as of like a couple of days ago, because I think somebody committed a new stream, but I'm not sure. There are a lot more in the works, so this list is just going to keep growing. You can view this on the reference guide, and there's a link on the last page for it. Okay. There are going to be a lot of streams where it has sort of proprietary business logic, and you don't want to share that with anybody, and you just want to keep it internal. To do that, you can expose your streams in your config file. So in the config file, you can give an expressible tag, give it the function name, so tuple number, and then tell it which class implements that. We don't care where this class is, what package it's in, et cetera, et cetera. You just have to, it just has to exist on the class path. A comment about this, if you decided, I don't want to call the inner join stream inner join because my users don't know what an inner join is. I just want to call it join. If you were to say expressible name equals join and then the implementation of the inner join class, then join now becomes a valid function name for you. And it will override the inner join that's already in, that was in there by default, right? So you can override the names if you want to. I wouldn't suggest that you do that, but there are cases where you might want to. All right, so I'll take some questions. We just ran out of time, but I'll stay around for some questions. The reference guide, that's a link. We've got sample code for the 3 streams that we looked at the read function. I've put them on GitHub so you can look at the full class implementation, and then a link to the rollup stream in the main Solr GitHub. Yes?
What is part of Solr? So it executes on the Solr server or
Yes. Yeah, so you send the stream request into a Solr, the stream handler. That said, it doesn't have to be the Solr instance where your collection lives. It could just be a worker that has no data in it, and you just have these powerful boxes to do the work. It is not happening on the client side, no. Yeah, it is happening on the Solr servers. Yes, you can. Yes, you can. On inner joins, there are merge joins where the data has to be sorted in the same way, and then there are hash joins where they don't have to be sorted in the same order, but there's a memory cost, because to do a hash, you have to read all of the data from one of them and hold it in memory, and then do your join off of that. So you have both options.
So I'm guessing that there's a parallel stream that I saw. So in the example where you do the voting records and all that,
Yep.
you could basically process those individual points in parallel.
Yes. Yep. Thank you.